In the previous video, we covered the shape of the trajectory of objects in a vacuum, given horizontal velocity, acceleration due to gravity, and vertical velocity. But we didn't cover true velocity and the energy of the object at different points in the flight. Kinetic energy, which is movement energy, is measured in joules, and so is all the other different types of energy. And they have a common unit of measurement because they can be converted between each other. For example, kinetic energy can be converted into gravitational potential energy. There are more types of energy, but I'll cover them in a different video. For this one, the only two we will be dealing with is kinetic energy and gravitational potential energy. We can calculate the kinetic energy of the object at any given point in the flight by using the equation E equals half of m. M is the mass of the object times v squared. V is the true velocity. We can calculate, this gives us the kinetic energy of the object, but we can calculate the gravitational potential energy if we know the initial kinetic energy, and then we minus whatever the kinetic energy is at the point in the flight we are at now, and that will give us our gravitational potential energy. A good way to think about it is that if there are two baskets, one is for kinetic energy and one is for gravitational potential energy. If we imagine there are grapes, and the grapes represent the energy in the object, they all start in the kinetic energy basket. But over time, the higher the object goes in its flight, they are taken out of the kinetic energy basket and put into the gravitational potential energy basket. If we know how many grapes there were in the kinetic energy basket initially, and if we can count how many are left over now, we should know how many are missing, and the ones that are missing are in the gravitational potential energy basket. And that's a metaphor for how we can calculate gravitational potential energy. To calculate kinetic energy, we will need to know true velocity, and in the previous video, we only used vertical and horizontal velocity. The way we can calculate true velocity from the horizontal and vertical velocity is by using a squared plus b squared equals c squared. Because if you look, for every single point in the flight, there is a right angle triangle. And the three sides represent true velocity, vertical velocity, and horizontal velocity. If we know the side representing horizontal velocity and the side representing vertical velocity, we can find the side representing true velocity. If we were to calculate the energy for all the points given in this flight, we would just need to repeat this equation over and over again. We are already given the mass of the object, 1 kilogram, and we know the velocity for each point. It is already written down, so we can calculate the kinetic energy. So for point 1, it's 16.8 joules. That's the starting energy, and that is all kinetic energy. But on point 2, we have lost some energy. It is at 12.5 now. This energy has been converted into gravitational potential energy because the object is higher now and it has lost some kinetic energy. And this repeats over and over again: 8.8, 6.5, 4.8, and 4.5. This is apogee. So now, the kinetic energy is not zero because we do have horizontal velocity in this flight, but now all our kinetic energy that was pushing us upwards has been turned into gravitational potential energy. So now our vertical speed is zero, and this is apogee. So we're going to start accelerating towards the ground again now. So this gravitational potential energy is then converted back into kinetic energy once more. So it's taken out of the gravitational potential energy basket and put into the kinetic energy basket. So the kinetic energy increases 4.8, 6.5, 8.8, 12.5, and 16.8. And as you can see, the kinetic energies are mirrored on both sides of the flight. If you were to write down the kinetic energies during the flight on a graph, you will see a trend in which the kinetic energy decreases at a decelerating rate until it reaches its lowest point, at which it starts increasing by an accelerating rate, just like the shape the flight creates when you throw it. And that is energies and true velocities of objects in vacuum trajectories.